You are probably familiar with the three main amplifier topologies of the bipolar transistor: the common emitter, common collector, and common base. And well, there are equivalents for other types of transistors as well. But what if I told you that there are a few derivatives of these topologies which can enhance the basic functionality? Hello, and welcome back. Today, I want to talk about a transistor amplifier topology which promises lower losses and better control of interface impedance: the lossless feedback amplifier. If you're curious about what this is and how it works, then keep watching. So let's start at the beginning. What is the problem that we're actually trying to solve? What is wrong with the fundamental three topologies? In general, any amplifier relies on negative feedback for stability and control. Some of the output signal is fed back into the input to establish a specific gain value. This is commonly done by using resistors on the emitter or a resistor in between the base and collector. While you could use other components, the main advantage of the resistor is the value stability with frequency, so any gain value that is set will be frequency independent. But using resistors for feedback has two major downsides. First, any resistor has an associated thermal noise. Usually, the more resistance, the more voltage noise you get. And second, simply passing the signal through the resistor will create heat, which is another way of saying that you're wasting some of your energy. So the issue we're talking about today is how do you create a frequency-independent negative feedback system which does not add noise and does not waste power? Well, you should use reactive elements. At least with the ideal components, there is no resistance in there. But this isn't all that simple either. Reactive elements have a tendency to have frequency-dependent properties. So, while you do commonly use things like inductors in the emitter or capacitors from base to collector to provide feedback for your amplifier, this method of using single components does not provide a frequency-independent behavior. For both the capacitor and inductor, the impedance is clearly frequency-dependent. It either increases or decreases. So, even for narrow frequency ranges, it's not really a constant. However, something interesting happens when you combine two reactive elements. So, to highlight this, I prepared a few simulations of circuits which can provide an output proportional to the input over a wide frequency range. To start off, if we look at a resistor divider, as long as you consider that it's built from ideal resistors, it's, well, ideal. We get a perfectly flat transformation ratio over the entire simulated frequency range. Then we could use the basic reactive elements: capacitors and inductors. This way we are creating lossless dividers, but these only work for a limited frequency range. As long as their reactance is smaller than the interconnecting resistances, we are getting the expected results. But when the two impedances are comparable, well, we are getting something else. The capacitor divider will provide a low-pass behavior, while the inductor divider will provide a high-pass behavior. The last type of component to look at is the transformer. So we can take the inductive divider and just couple the two inductors. So far, nothing interesting really happens. But using a transformer does present a few very important possibilities. So first of all, we can completely isolate the signal source and where the proportional feedback is going. Then by rotating the inductor, you can change the phase by 180 degrees. By adjusting the turns ratio, you can create both smaller and larger values of feedback compared to the initial source. And finally, a transformer can have more than two windings. You can combine and distribute signals into multiple parts of a circuit. So when it comes to building feedback circuits, using transformers offers unique possibilities which are otherwise impossible with the standard inductors, capacitors, or even with the resistors. So this will be the key component to the lossless amplifier. If you do wish to read about this amplifier in more detail, I highly recommend the original patent describing it. So this circuit was invented by David Norton and his colleagues in the 1970s. The patent describes the operation of the circuit as well as the various formulas needed for the design. But long story short, the amplifier is built around a common base configured transistor and a free winding transformer used to link the emitter circuit with the collector circuit. I also found this great paper by Chris Trask that goes into the details of lossless feedback amplifiers, though sadly this page is only available on the Wayback Machine. Anyway, this is also a paper that describes the operation of this amplifier and how it can be enhanced. Now, regarding the design of such an amplifier, I do not want to go into too many details other than mentioning the transformer, which anyway is the main element to be designed. So since this is a common base amplifier, the free resistors will be used to set the operating point, nothing special so far. Then the inductor in the emitter is there to reduce losses and provide a high impedance over the entire operating frequency range, and the transformer is therefore the star of the show. This is usually defined as having a turns ratio of 1 to n to m, where 1 is the number of turns in the emitter circuit, and n and m refer to the collector circuit and represent multiples of the turns in the emitter. Then the circuit is finished off with some capacitors, one for stabilizing the base voltage, and two for coupling the signal into and out of the amplifier. So based on this arrangement, we can say that the input impedance is related to the load impedance and the various ratios of the transformer. And second, the voltage gain is related to the upper end, the M part of the winding. Now, while you can do whatever you want with the turns ratios, there is one very specific case of interest, when the input and the output impedances are the same. So for example, if you need a gain block with 50 ohms on both input and output. Well, we can get this with the following turns ratios, and these correspond to some specific gain values. So one thing to notice is that if we're looking for gain, you will need some really large turns ratios. So the point of this amplifier isn't really to provide tons of gain, but rather to be low noise and efficient when used as a very first stage in a larger chain. We can first test this type of circuit out in the circuit simulator, of course. So what I prepared here is a version where both the input and output ports are the same impedance, 50 ohms, and the gain is set to 9.5 decibels. I adjusted the resistor values to have the amplifier stable with an operating point at 9 volts, at which the transistor has a collector current of about 16 milliamps. And the transformer follows a turns ratio of 1 to 5 to 3. This is done by multiplying the emitter inductance by 5 squared and by 3 squared. To fully verify the circuit's operation, I first ran an AC type of simulation. So here, we can see that the incoming signal of 2 is divided into half to 0 decibels, and then the output is about 9 decibels above this. So the gain is respecting our expectations. And well, to get the exact impedance values, I also added in a .NET statement to check the impedances. So if we plot these out, we can see that we are very close to the 50 ohm mark over the frequency range in which the response is flat, roughly from 2 to about 20 MHz. Before and after, we are getting various nonlinearities because of the exact inductance values, but also because of the non-ideal transformer couplings. So with the connected source and load impedance, the amplifier is matched on both ends, at least in the linear range. Therefore, in the simulator at least, the circuit is working as expected. Now, to verify the circuit works as advertised, I also built it in real life, following more or less the same schematic as used in the simulator. So I used the same component values, just that for the transistor, I used a BC108 that I had around. This is quite a pretty looking transistor, so I wanted to use it for something. Now, if you do build such a circuit, one of the things that becomes painfully obvious is that the transformer is not a standard part. You will have to make it yourself. I built this over a small toroid And if you want to get good coupling in between the windings over a wide frequency range, well, the emitter winding needs to have more than one turn. This subsequently makes everything else quite large. So I used 4 turns for the emitter circuit and 20 and 12 for the collector circuit. And this is what the transformer ended up looking like. To test it out, I hooked the board on one side to a power supply providing 9 volts, and on the other to a 50 ohm signal generator, a fixed 50 ohm load, and a couple oscilloscope probes to measure the input and the output. The main measurement objective being to check the input impedance and the gain over a frequency range. For the actual tests, there are a couple things we can do. First, to make a quick test, we can use the signal generator to just inject a sine wave, say a 200 mV 1 MHz sine wave. And if we turn this on, and also turn on the first channel of the oscilloscope, we can see a value of roughly half. So we are getting a sine wave of 90 millivolts. So this is exactly the amplitude that we're expecting when the generator impedance is matched to the circuit impedance. And well, if we also turn on the second channel of the oscilloscope, the output is roughly 250 something millivolts. So if we divide the two, we get a gain of about 2.8, if turned into decibels, is about 9. So very close to what we're supposed to be getting. Now, this is a single frequency measurement, done at 1 MHz. But to get the full picture, we can do a proper wide frequency Bode plot. So if we run such a measurement from 50 kHz up to 25 MHz, and well, wait for it to conclude, we can now first focus on the first channel of the oscilloscope. Here we are getting our -6 decibel amplitude more or less in the 1 to 10 MHz range. So we can make the assumption that the circuit impedance is 50 ohms in this range. And well, before and after, it drops to some lower impedance value. But then, if we also turn on the second channel of the oscilloscope, this will tell us the ratio of input to output signal. And here, we are getting a value of around 9 decibels. So it's not the 9.5 decibels that we're supposed to be getting. We're slightly lower than that, but it's really close. And this is maintained flat more or less in the same region in which the input impedance is flat. So we are getting a bit of deviations in the behavior compared to the simulator, but I guess this is mostly due to not simulating very accurately the couplings that are occurring in the transformer, and maybe some losses were skipped. But regardless, the amplifier is working almost exactly as expected. So the amplifier is doing what it's supposed to, even the one that I built. But this is not a very commonly used topology. Where would you actually see something like this in real life? Now, one of the places in which I found this type of amplifier mentioned was this paper, where the amplifier is analyzed as a possible solution to a low noise amplifier for radio astronomy. So the paper analyzes the performance of the amplifier to see how it would fit the long wavelength array. Other than the description of the circuit and the analysis method, you will of course find the schematic used, as well as the various performance parameters obtained. So this is quite a nice analysis on what such a circuit can actually do. The conclusion is that the amplifier is indeed adequate, but I don't think that they ended up actually using it, probably because of the transformer's complexity. And in the end, I guess this sums up such an amplifier. While it does provide some very important performance advantages, it's still quite a difficult build, mainly because of the transformer. Constructing that specific component is highly labor intensive since it's such a complex part. It can be done if you just need a couple amplifiers, but it's not something you would want to mass produce. So the lossless amplifier does have a place in the world, even if it's a bit niche. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.